Swayam Prabha. Digital India. Educated India.
Welcome to the 6th lecture in mechanics of materials. Continuing from the previous lecture, we are going to look at the concept of stress. In the previous lectures, we looked what traction is. Traction was defined as the distributed force acting over a cut surface or boundary of the body, and we said that the traction will be denoted by T's of n, and this in general would be a function of the position vector of the material particle in the current configuration time t and the normal n, the normal to the cut surface. We also saw that the traction on two opposite cut faces should be equal, and hence T of n plus T of minus n should be equal to 0 at a particular point. This is essentially the Newton's third law of motion, that every action has an equal and opposite reaction. So, we saw that these two conditions have to hold, and hence we said that the traction would be linearly related to the normal n. Related to n, and hence we went about understanding what that linear relationship is, which we called it as second order tensor. This linear relationship between two data line segments was called as second order tensor. Order tensor was defined as the linear function between two directed line segments also called as vector. Okay. So, we saw that there is a tensor product which goes into representing a second order tensor. So, A for example would be represented as A j dot ei tensor product Ej, right. So, this is what we saw in the last class, where this is the components of a second order tensor Aij, and this is like the basis vector 1 0 0 0 0 0 0 0 0 or 0 1 0 0 0 0, like that it will form a basis vector, basis matrices. Okay. So, that is what we saw in the last class. In today's class, we said that T would be linearly related to n. We said that T's of n would be linearly related to n, and that gives rise to the definition of stress. In particular, we define T's of n to be related to n through a stress tensor. This is called as stress tensor. Why I am defining it with a transpose? The superposed T denotes, this denotes transpose of the tensor. Okay. So, let us go about understanding how to find the components of the stress tensor, or in other words, what does the components of the stress tensor mean? That is what we are trying to find. Okay. So, we said that x being mapped on by a y is example of linear mapping the data line segments y to data line segments x. Now, let us go about looking at the traction. We wrote traction as sigma transpose n. Now, I am interested in finding the components of sigma, components of the tensor sigma. Okay. So, now what is sigma ij? Sigma ij would be sigma ej dotted with ei. Going back to the definition of the tensor, a ij is a ej dotted with ei. We find that sigma ij would be sigma ej dotted with ei. Now, let us understand what the transpose means. This I have explained in lecture 3 also. So, if I have a dot a b, this is same as a transpose acting on a dotted with b. This is the definition of transpose of a second order tensor. Okay. So, basically if you want to take A operating on B to A operating on A, that will come with a transpose symbol there. Okay. Having understood this, let us do the transpose operation here. This will be sigma transpose ei dotted with ej, that is nothing but T's of ei dotted with ej. So, sigma ij can be interpreted as the jth component of the traction acting on the ith side. Let us understand what this means. I have a body, first I have a coordinate system, Ex, Ey, Ez, and I have a body now. I am interested in finding the stress at this point. What do? I go about isolating an infinitesimal cube about that point. I am enlarging this cube. I am enlarging that cube. Now, this face as Ex as is normal, this face as Ex as the normal. On this face there will be a traction that will be acting, there will be a traction that is acting like this. This is T's of Ex. Okay. There will be a traction T's of Ex acting like that. Now, what do? I find the components of this traction by projecting it onto Ex, Ey and Ez. When I project the components of the traction onto Ex, Ey and Ez is sigma xx. How? Let us do the operation. I have sigma would be say sigma xx, sigma xy, sigma xz, sigma yx, sigma yy, sigma yz, sigma zx, sigma zy, sigma zz. Okay. Now, the components of it is sigma transpose acted upon by Ei. So, T's of Ex would be sigma transpose Ex. So, this will be sigma xx, sigma xy, sigma x z, sigma y x, sigma y y, sigma y z, sigma z x, sigma z y, sigma z z into 1 0 0, that is going to give me sigma x x, sigma x y, sigma x z. Okay. So, this is T's of E x. So, the component of E x along E x direction is sigma x x. Similarly, sigma x y would be the component of T of E x along E y direction, which will be this will be sigma x y, and similarly sigma x z would be the component of this traction along the z direction. So, this will be sigma x z. Okay. So, what does the first index indicate? The first index indicates the normal to the surface on which the stress components are written. The second index indicates the direction of the force along which the direction of the force. Okay. If I write sigma I j, the first index, this denotes the normal to the, it indicates the normal to the surface, and the second index indicates the direction of the force. The second index indicates the direction of the force. Okay. So, basically now how do I know the direction of the direction that I have indicated is the direction for the stress components? Sigma x x, sigma x y and sigma x z are assumed to be positive. Since they are positive numbers, they should be along the coordinate direction in which the coordinate system is. Now, let us go a step further and then see what happens in the other phase. Let us see what happens in the other phase. This phase, the normal is like this is negative E x direction. Okay. So, now I have T of minus E x, that would be sigma x x, y x, sigma z x, sigma x y, sigma x z, sigma y y, sigma y z, sigma z y, sigma z z acted upon by minus 1 0 0. Now, this will give me T's of minus E x as minus sigma x x minus sigma x y minus sigma x z. Since sigma x x, x y and x z are assumed to be positive numbers, now these are negative numbers, indicating that the direction of the stress, direction of the force in the negative phase should be opposite to the orientation of the coordinate system. Okay. And hence sigma x x would act like this, or first let me draw the T's of minus E x should have the same magnitude, but opposite in direction. So, these two are parallel, opposite in direction, and sigma z z on this face, sigma x x on this face would be opposite to the coordinate system, because sigma x x is positive and we got a negative sigma x x, and hence we are drawing it opposite to the direction of E x. Similarly, sigma x y, what we got was minus sigma x y, and hence it would be opposite to the coordinate system. So, this is sigma x y. Okay. Similarly, sigma x z should also be opposite to the coordinate system, and hence this will be sigma x z. Okay. So, in two phases we got the orientation of the stresses to be opposite to each other, but same in the magnitude. In other words, what this tells us is the tensile stresses are positive. Sigma x x and sigma x s are opposite direction, they kind of pull the cube, and hence it is positive. This does not mean that we assume tension as positive, it is a consequence of assuming a coordinate system and writing the components of tensor with respect to that coordinate system. Okay. Now, let us move further and see what happens to this phase. To the top phase, the normal is Ey, and the traction that is acting on that face would be something like this, T's of Ey, and the component of this traction along the normal direction would be this, that will be sigma Yy. Okay. The component of the traction along the x axis would be like this is a positive direction, positive normal, the number is going to be positive and hence this direction to be along the direction of the coordinate system. So, this is going to be sigma y x, right. The normal is y, it is acting along the x direction. So, it is sigma y x, and then the third component of T's of Ey is going to act along the z direction and hence this is sigma y z. Okay. So, we have seen what the stresses are on the Ex phase, Ey phase. I am now just going to draw components of the stress on the Ez phase. This phase I am going to draw it. I leave it for you to understand how I got these things. It should be clear by now how I am getting these stress components. So, you have Ez acting on this phase. So, the traction would be acting in some inclined manner like this is T's of Ez, and now the component along the normal direction would be sigma Zz, and then this component would be sigma Zy, and this component is going to be sigma Zx. Okay. That component is going to be sigma Zx. That is the reason why I drew sigma xy and yx with the same color. They will be same in magnitude, which we will show later. Hence, the stress tensor is a symmetric tensor. Okay. Now, we understood how you get the components of a stress tensor. The way we get the components of stress tensor is we go to a point in the body, draw an infinitesimal cube such that the sides of the cube have its normal along the coordinate directions. Once you get the sides of the cube oriented along the coordinate directions, then the sigma xx, sigma yy and sigma zz would act along the normal to the each of the x, y and z faces, and hence they are called as normal stresses. These three are called as normal stresses because they are acting normal to the face. Okay. And the remaining three components are called as shear stresses because they are acting parallel to the surface. Okay. So, this is how you find the components of the stress matrix or stress tensor.